Self-healing CI/CD with AI agents. In the next several minutes we'll build an agent that reads a failing pipeline, finds the root cause, and writes the fix. And we'll go deep on every concept behind it, from how the model thinks, to structured outputs, to MCP. Start with the pain. A build fails, usually for a boring reason: a drifted dependency, a flaky test, a missing config. You already know how to fix it. The expensive part is the context switch. Stop what you are doing, open hundreds of lines of logs, and hunt for the one line that matters. Multiply that across a team, every day, and it's a real tax on your time. Reading messy text and extracting the signal is exactly what a language model is good at. Here's the plan. First, what a language model actually does, and what makes something an agent. Then we build the agent piece by piece: the schema, the system prompt, and the call. Along the way we'll cover structured outputs, prompt engineering, adaptive thinking, and the agent loop. Then MCP and connectors, so the agent can act. And finally, how to run this safely in production. So, what is a large language model, really? At its core, it's a next token predictor. Give it some text, and it predicts the most likely next chunk, over and over, to build a response. It was trained on a huge amount of text and code, so it has seen millions of stack traces and error messages. That's why it can look at a log it has never seen before and still recognize the pattern. We are not asking it to run your code, we are asking it to read and reason. Now, what turns a model into an agent? A chatbot answers a question. An agent is given a goal, reasons over some context, and produces an action. Here, the goal is fix the build, the context is the failing log, and the action is a patch. Add tools, and the agent can go one step further and act on the world. We'll get there with MCP. Here's the whole system: 4 moving parts. A failing log comes in from your CI and agent. A single model call with a senior engineer persona reads it. It returns a structured, typed fix, and that fix goes to a human for review, or straight into a pull request through a connector. Let's build each piece in code. Setup is refreshingly small: 1 library and 1 API key. Pip install the Anthropic SDK and Pydantic. Pydantic is how we'll describe the shape of the answer we want back. Export your key as an environment variable, and we are ready to write code. We start with the model. We import the SDK and Pydantic, and pick a model. Think of the model as the reasoning engine. A bigger model reasons better but costs more. So for something you run on every failed build, you can drop to a smaller, faster one. This single line is the only place the model is named, which makes it trivial to swap later. Here's the core trick that makes this reliable: structured output. Instead of hoping the model writes nicely formatted text, we define a schema, a Pydantic class that describes exactly the fields we want: root cause, category, confidence, the file to change, a patch, and an explanation. Notice that category and confidence are not free text, they're fixed sets of allowed values. Why does this matter so much? Compare the two worlds. Without a schema, the model returns a paragraph of prose, and you are left writing brittle regular expressions to pull out the pieces, which break the moment the wording changes. With a schema, you get back a real, typed object: fix.confidence, fix.patch. Under the hood, this uses JSON schema to constrain the output, so the fields are guaranteed to be there, and guaranteed to be valid. That is what lets you build real logic on top. Next, the persona, the system prompt. This is the model's standing instruction. We tell it it is a senior site reliability engineer, to find the root cause, not just the surface error, to propose the smallest safe fix, as a git-appliable diff, and critically never invent files or dependencies it cannot see in the log. That last line is the whole game, and it has a name: prompt engineering. A language model will confidently make things up if you let it. We call that hallucination. So we don't just ask for a fix, we set boundaries. Find the root cause, don't invent things, and if you are unsure, say so, and lower your confidence. A calibrated, I'm not sure, is far more useful than a confident, wrong patch. The prompt is your first and cheapest guardrail. Now we make the call. Messages.parse sends the log to the model, and the output format argument hands it our schema. What comes back is not a blob of text, it's a validated proposed fix object, ready to use. One call, one diagnosis. It's stateless and cheap, which makes it easy to trigger only when a build actually fails. You'll also notice thinking, set to adaptive. Modern models can reason before they answer, a kind of internal scratchpad. Adaptive thinking lets the model decide how much reasoning each problem deserves. A one-line typo gets a quick answer. A tangled dependency conflict across several packages gets more thought. You get better answers on the hard cases, without paying for deep reasoning on the easy ones. So far, our agent does one pass. Real agents run a loop. The model looks at the goal, decides it needs information or an action, and calls a tool. The tool runs, maybe it reads a file, or runs the tests and returns a result. The model reads that result and decides the next step. Reason, act, observe, repeat, until the job is done. Tools are how an agent reaches outside its own text and touches the real world. Which brings us to the big one, MCP, the Model Context Protocol. Historically, every tool needed its own custom integration, glued to one specific app. That doesn't scale. MCP is an open standard. Think of it as a USB port for AI on one side, your agent, the client, on the other. An MCP server that exposes a set of tools and data in a standard shape. Any agent that speaks MCP can use any MCP server. Write the connector once, and every agent can use it. In practice, you connect the servers you need, a GitHub connector, a Slack connector, a Jira connector. Suddenly our agent goes from printing a patch, to opening the pull request itself, commit the diff, push a branch, open the PR for review. And here's the crucial part for security. The credentials live in the connector, outside the model. The agent asks the connector to open a pull request. It never sees your GitHub token. That boundary is what makes it safe to let an agent act. Let's see it run. We feed in a real dependency conflict, Flask and Workzode, pinned to incompatible versions. The agent responds. Root cause, nailed. Category, dependency, confidence, high, and an actual diff you can apply. Red, 2 green hands-free triage, in seconds. Step back for a second. Where does this sit? This is the heart of AIOps, using AI to run operations. The same pattern powers alert triage, log analysis, and incident summaries. It's also LLMOps in miniature, a prompt, a schema, guardrails, and cost control, wrapped around a model. And notice the shape. The agent does the tedious triage, and a human makes the final call. Augment the engineer. Don't replace them. Before you wire this to production, 4 guardrails. 1. Keep a human in the loop. Auto apply only high confidence, low risk fixes, always behind review. 2. Least privilege. What reads your logs must not hold your deploy keys. 3. Gate it. Run only on failed builds, not every green one. And 4. Cost. Cache the system prompt, so repeated context is nearly free. Do that, and each triage costs pennies. So, what makes this work? Structured outputs make the answer reliable. A strong system prompt makes it safe. Adaptive thinking makes it smart about the hard cases. And MCP connectors let it act, not just suggest. That's a self-healing CI agent, end to end. In the next episode, we give this agent the GitHub connector, and let it open the pull request by itself. The full code is in the description. If this helped, subscribe to AIOps Academy, and I'll see you in the next build.